So I would like to talk some more about computing functions with Turing machines. That's what we were talking about last time. I guess we've only got a few days left. I don't think I have anything worthwhile to say about it. It's been great. We could have a little campfire at the end maybe, but yeah, we're not having another test on the last day or anything like that, so it's just regular class until the final exam. We will be, we'll have homework due on Tuesday as usual. I can say, I'm sorry I've been a little bit behind with the homeworks grading lately. I graded the most recent one, but not the one before that, so I'll get to it soon enough. All right, I hope that's not been an inconvenience to anybody. Okay, let's do it. So what we were talking about last time is using a Turing machine to compute a function. And the way that that works is the machine, we start the machine with, say, the input x on the tape, and then finish with f of x on the tape. Right? If there is a Turing machine that can do that, then that function is called Turing computable. And that machine, we say that machine computes the function f. And we were doing some simple examples of computable functions. There were some sort of simple string examples of functions on strings, like put an a at the beginning of a string or something like that. And then we also talked about some more kind of recognizable arithmetic functions using binary numbers. But the most complicated ones we did was f of x equals x plus 1, a function which just adds 1, and then we also did a function which subtracts 1. When you tell your friends at lunch, as you always do, about this class, and you say, oh yeah, we learned how to make a machine that adds numbers, they would say, oh yeah, like can it do like 2 plus 7? And you would say, well, no, actually it only adds 1. So today I want to talk about, can you do like 2 plus 7? So this would involve, what about, really the issue is, what about functions of, let's say, 2 parameters? Because this is really the big difference when your friend says, well, what about 2 plus 7? You could probably, just like we did last time, you could make a machine that adds 2 or a machine that adds 7. But a machine that takes the 2 and the 7 and adds them together, that's a different sort of a thing. So that's what I want to talk about today. Functions of, that's what I mean by 2 parameters. That is a function where you plug in 2 inputs and the machine sort of somehow combines them together into a single answer. All right? Like I would say something like, plus of 5 and 13 equals 18. Ordinary people wouldn't write plus that way, but, to a programmer, this doesn't seem all that weird. How are you going to do that on a Turing machine? Because the Turing machine just has one big tape. One way to do it is you could write the 2 inputs on the tape with some kind of a separator. That's what this would be called. Like 5, 1, 3. Like the comma is actually part of the input, and there's a comma on the tape as one of the letters that's written on the tape. And then your machine, if you think about how the Turing machine would have to work in order to handle these 2 numbers, it would have to be like, certainly if they were several digits each, if they were like this, I didn't mean to make them almost the same, but if they were several digits long, the tape, in order to add these 2 numbers together with the comma in between, would have to kind of constantly be going back and forth, because really what you do is first you would add the 5 and the 8, and then based on that you would then add the 3 and the 3, and then add the 1 and the 1, and you'd have to keep on going back and forth across, using the comma as like your sort of signal that you're part of the one input versus the other input. This is very complicated. It's easier, can I just say, for this kind of arithmetic at least, for adding and other, I will say adding, etc., it's often easier to stack the inputs like actually write these two numbers as, I'm going to call these stacked inputs. Each digit, you line them up as part of the input. So those, I'm writing them like fractions, but they're not, I don't mean fractions. I just mean a 1 on top of another 1, and a 3 on top of another 3, and a 5 on top of another 8. This is just to arrange them on the tape so that you don't have to keep on going back and forth across the comma or whatever separator you want. And you can just treat this so the tape, looks like this, where in this location on the tape you have this stacked 5 and an 8, and here you have a 3 and a 3, and here you have a 1 and a 1. All right, this is just a matter of convenience. It's easier to process inputs that are stacked in this way, if you intend to add them together, because this is how you add them together anyway. You would imagine them to be stacked up. All right. So let's try and do some examples of two parameters which are stacked in this way. So let's try, and of course we are also going to do everything in binary because that's easier than dealing with 10 different digit symbols in base 10. All right, so it's often easier to stack the inputs like this. So in binary, the alphabet that we're looking with, or the input alphabet, is stacks like, these are all the possible stacks that you could ever encounter in binary, right? Those are the only possibilities when it comes to stacking two binary digits. Two bidgets, if you will. That was apparently an early term for binary digits. I read that once. Bidgets. And then they decided to use an abbreviation for that. Anyone know the abbreviation for bidgets? Actually, everybody knows. They are now called bits. Tell your friends at the club. No, actually, bits is short for bidgets. Yeah. They love the bidgets at the club. All right. So the input alphabet looks like this. They stacks like that, right? And I want to talk about doing a function which takes stacks like this as the input and then gives you some kind of answer. So how about let's try a Turing machine for, this is referred to as, this is a very simple arithmetical operation, bitwise AND. That is, you take two binary numbers and you just go down bit by bit and you combine the individual digits with the logical operation AND. All right, so the idea is if I have something like 0, 0, 1, 1, 0, and 1, 0, 1, 0, 1, you line them up bit by bit, and then you combine each bit using the operation AND. So this would look like, if I were trying to do this by hand, I would do something like line them up 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, and then I do something like this. It's like you're adding them together, but I'm adding them using the operation AND, which is, this is like from the AND operator in logic, interpreting 0 as a false and 1 as a true. So 0 and 1 is 0. When I'm doing AND, the answer is only 1 if both inputs are 1, and it's 0 otherwise. So this is a 0, this is a 1, this is a 0, this is a 0. All right? So that's the operation that I want to make my Turing machine do. So in this example, the Turing machine would start with, on the tape, it would start with these stacked bits. Right? That's the stack of these inputs. And then it would end with the answer on the tape. 0, 0, 1, 0, 0. Right, that's the idea. All right, let's see if we can do it. So I will start like that. I don't know if this seems complicated to you. Actually, I can do this Turing machine using one state. It's true. All you need is one state. What I'm going to do is, if I were adding them together, I would start by going all the way to the right and then do digit by digit, moving leftwards. That's because adding has carries, but this bitwise AND never carries or anything. So actually, you don't need to do it right to left. You can do it left to right if you like. And so I'm going to do it left to right. I'm going to use one state, which means every arrow is going to be a loop because I'm only using one state. So there's really, it's just one arrow like that. And you just have to say what happens. So for example, I'm going to go 0, 0, slash something, comma, something. Every move is going to be to the right. It's just a matter of saying, okay, if you see 0, 0 on the tape, what do you want to write as on the tape in that spot as the answer? What do you think? The answer is 0. Yeah, if you see 0 and 0 and you're combining them using AND, the answer in that digit should be 0. And then you move to the right onto the next digit. There's no need for fancy states or anything like that because your machine is just going to do exactly the same thing in each position on the tape, right? What about, so that was if you see 0, 0, I need to just write down the various possibilities, right? And say for each one what the answer should look like. So what is 0, 1? That should be 0 also. 1, 0 should be 0 also. And then 1, 1 should be 1. And I move to the right. All right. Do we need some kind of, what if you see a blank, or what about the accepting state or anything like that? I would say you don't need an accepting state. Remember the way that we write these Turing machines, which are meant to compute functions, they don't have an accepting state. The whole idea is you start with something on the tape, it does its business for a while, and then when it stops, you should see the answer on the tape. So this is going to continually move to the right through these stacked digits. Eventually it will hit a blank. I put no arrow for blanks, and so it will just stop. And that's it. That's what you want it to do when it gets to the end of the input, right? It should stop, and you should see the answer on the tape. So this is the bitwise AND Turing machine. Very simple, in my opinion. All right? Could you imagine doing bitwise OR? The answer is yes. It would look exactly the same, only these answers would be different, right? They would be 0, 1, 1, 1 if you write them in this order, all right? Very simple to do those kinds of bitwise and OR. There's something called XOR, the exclusive OR, which is also very similar. More interesting would be, let's try bitwise add. Now this one is a bit more complicated. Bitwise add. This is actually going to add together two binary numbers with carries, and the carries is really what makes it more complicated. Bitwise add with carry. All right, let's see if we can do that one. So in this, maybe just using this same example, let's try to add these ones instead of anding them. It would be these guys I'm going to add. So as we all know, first of all, we should start adding in the rightmost position. Yeah, is that a question? Sorry.
I'm a little bit confused how you got your answer, because I just put like both those in like an addition, and it became 1, 1, 0, 1, 1 instead of 0, 0, 1, 0, 0.
Here.
Yeah.
Yeah, because this was not addition. This is and.
Oh.
And is not like addition, because like for instance, and of 0 and 1 is 0. But if you were adding, you would get 1 here. So it's different operation. But now I wanna add them. All right. So this is a new example. This is quite a bit more complicated because it involves carries. The bitwise AND doesn't carry, so it's a lot easier. So what's the answer when you actually add them? I go, you start in the rightmost digit. I go 0 plus 1 is 1, no carry. 1 plus 0 in the next digit is 1, no carry. 1 plus 1 is 2, which in binary means I have to carry. So I put a 0 here and carry a 1. And then I go 1, 0, 0 is 1. And then 0 and 1 is 1. And this is the sum of those two binary numbers, all right? You have to carry sometimes. But I will point out, actually, if you're adding two binary numbers together, you can only ever carry a 1. There's no such thing as like carry a 2 here. Because in order to carry a 2, well, first of all, there isn't even such thing as 2 in binary, but that would be like carry a 10. But anyway, that can't happen because the biggest sum you could ever get would be a 1 plus a 1, which carries a 1. You could, in theory, get a 1 plus a 1 with a carry from a previous step, but even that would add up to 3, which looks like 1, 1, and so you put 1 here and carry 1. So anyway, there's never a bigger carry than just a carry of 1. So the diagram I'm going to use here involves two separate states for the addition. So there's a preliminary step, which is the move all the way to the right step. We have to do that first because, as everybody knows, you have to start adding from the rightmost digit. So I need to go to the right through everything. This is kind of a pain to write down, but I go through all of these things, leaving them the same. 1, 1, 1, 1, R. Finally, when you see blank, that means you're at the end. I go BBL. And now I'm ready to start. So that's just a little preamble to move all the way to the rightmost end of the numbers. Now we are in position at the rightmost digit. And I'm going to have basically two states over here, which I'll just to help, I'm going to give them little names here. This is a no carry, and there's also like a carry version. That is to say, if there has been a carry from a previous step, all the answers in that digit will be different. They'll be 1 higher. Versus if there has been no carry from a previous step, then the answers will not be increased by 1. And I begin the computation in the no carry state. That's because in the rightmost digit, when you start adding, there is no carry from any previous step because there aren't any previous steps at that point. So I begin in the no carry state. And again, we just have to think about all of the possible pairs of bits you could have, all the possible stacks of bits that I could have, and what happens according to them. For instance, how about this stack? If it was 0, 0, and I'm in the no carry state, what should the answer be in this digit? This would be 0 plus 0. You can show me the fingers if you like. I see people showing me the fingers. It's 0, yeah. 0, if I'm in the no carry, then 0 plus 0 equals 0. And you should also think, does that require a carry to the next digit or not? The answer is no, it doesn't. If I'm adding 0 plus 0, there should be no carry. So this is going to be a looped edge here. 0, 0. The answer is 0. And I'm going to put L. All the movements will be to the left because this is how you add numbers digit by digit. All right? So this says if I'm adding 2 zeros in this digit, the answer is 0. I move to the left to the next digit, and I do not carry on to the next digit, which is why this arrow goes back to the no carry state. All right? What about 1 and 0? I think actually 1 and 0 is also this same loop. 1 and 0, the answer should be 1, and again, there's not a carry. If I'm adding 1 and 0 in this digit, the answer is 1, because 1 plus 0 is 1. And then I move to left to the next digit. Also, 0 and 1, of course, is the same. The answer is 1, and I move left to the next digit. All right? 1 and 1 is different. Can anybody say what's the difference? 1 and 1? Yeah?
Is that you're carrying 1?
Yeah, 1 and 1 results in a carry. You should also say what is the answer in that digit. If I do 1 plus 1, you have to write an answer in this digit, and then you also carry. So what's the answer that you write?
0.
I see the fingers again. Yeah, it's 0. So I'm going to put, that goes like this, because it causes a carry in the next step, and it says 1, 1, the answer is 0, and I move to the left. So when you see 1 and 1, you get 0 as the answer in that digit, but then you have to carry. And so I send it over to the carry state. All right? These are all my arrows from the no carry state. Now we have to think about what there are 4 of them, right? And I need to make 4 different arrows from the carry state, depending on what the various stuff should be. So let's talk about 0, 0 again from the carry. You have to think, first of all, what is the digit that results from the addition, 0 plus 0, with a carry from the last step? And then also, will this generate a new carry for the next step or not? Anybody think you know? First of all, how about, what's the answer? If I'm adding 0 plus 0, but there has been a carry in the previous step, what should the answer be? I see the fingers again. They're showing me this one finger. Yeah, if I'm adding 0 plus 0, but there is a carry from the last step, then the answer in this digit should be 1. And should I carry to the next digit? The answer is no, because you just added 0 plus 0 plus 1 equals 1. It doesn't carry over to the next. So that means from here, I'm going to put an arrow like that. If I added 0 plus 0, the answer should be 1. And of course, I move left. All my movements are left. All right. Okay, what about 1, 0? We have to think in the same way. If I have 1, 0 with a carry from the previous step, can anybody say what's the answer in this digit and does it carry or not for the next step? 1 plus 0 with a carry. Maybe someone I haven't heard from yet. What do you say?
0 with a carry.
Yeah, 1 plus 0 with a carry results in answer 0 for this digit with a carry to the next digit. Because 1 plus 0 plus a carry adds up to 2, which you would write as 1, 0. Between 0 and this digit and you carry. So that looks like this. 0 on this digit, and yes, you do carry. Like so, right? That's why it's a looped here, because we do need to carry into the next digit. All right? 0, 1 is the same. Everybody knows that. 0, 1 behaves exactly the same. 0 plus 1 is exactly the same as 1 plus 0. So all of that will be the same. And then what about 1 and 1? If I have 1 and 1 with a carry, that's a total of like 3 I'm adding up. And so 3 in binary looks like 1, 1, which means I write a 1 in this position and I also carry to the next one. So that goes here also. 1, 1, 1, L, like that. Ooh. All right. This is basically it. There's one more little thing that I want to put in here. Anybody feel like something's missing? It's not an accepting state. We don't need an accepting state. You got an idea?
Is it that once you see a blank, he needs to go somewhere else?
Yeah, it has something to do with blanks. What if you, our previous example didn't have anything about blanks. That's because I said, you just go digit by digit, eventually get to the end. That just means you're done. And so you stop, which is what this machine will do when it sees a blank. It just stops, and that's what you want it to do. I think actually there's one case in here in which you will get to the end, but you're not actually done yet. You shouldn't. Anybody feel? Yeah?
If you're carrying, then you need to make blank 1.
Yeah, if you are carrying into the last digit and you see blank, that is, you're adding numbers together in such a way that it actually carries over into a new digit at the end, right? In that case, you will encounter a blank and you should change it into a 1. You only do that if you are carrying. So that's an arrow from here, not from the other one, because if you're not carrying when you get to the end, then you don't do anything. But if you are carrying when you get to the end, you see a blank and you change it to a 1. And that's really the end. This is the final carry if somehow your addition produces a new digit. You'll have to carry that 1 digit into the end. Is it possible your addition could produce more than 1 new digit? Anybody have feelings about that? I think, like, in terms of binary, digits are not all that much, right? I mean, maybe you end up, like if you're adding two ordinary base 10 numbers together, you could imagine making a new digit with value 7 or something. If that happened in one of these, then wouldn't that have to be spread across several digits at the end? Anyone have a feeling about this? You got feelings?
I don't think it would change.
You don't think it would change? You mean this machine could still handle that? Well, if you change one blank to a 1, it's just going to stop after that, right? According to the way that I wrote this. Now, if it actually had to continue writing new ones into blanks, then, well, this isn't going to do that the way it's written right now. Anybody else have feelings? I appreciate Will is very open with his feelings. And I'm fairly open with my feelings too, I guess. I think this is not possible. I don't think you can make more than one digit at the end because just a few minutes ago, I seemed to convince you that the only possible carries is a carry of 1. And that means you can't carry too much into the last step, right? Every step can only possibly result in a carry of 1. And I hope you still believe me when I say that. Like digit by digit, you can only ever carry 1. There's no way to add 2 digits here that results in a carry of 5 or something like that. So it means by the time you get to the end, there might be no carry, there might be a carry, but whatever it is, it's just a carry of 1. And so that will be adequately handled by changing a single blank to a 1. Right? Yeah?
Does the machine account for if you are carrying on a 1 plus 1?
Yeah, I think so. So here, this says if it's a 1 plus 1 with a previous carry, then really you should say that sort of all adds up to 3, which in binary would be a 1 and a 1. So you put the 1 here, and then you also carry. So, yeah, I think it works. All right. I got one for you to try. Can you try bitwise subtracting? It should be fairly similar to this. I would encourage you to think of it in terms of digits which either borrow or do not borrow. So let's try bitwise subtract. And I'm going to say parenthetically, let's just assume that the answer isn't going to be negative. Just because you'd have to make some choices about how you want to indicate a negative answer, and I don't want to get into that. So let's just assume that the subtraction will work properly without, that is, I suppose the first number is bigger than the second number. You know what I mean. I would suggest it's going to look very much like that one. It's just you have to think through the individual arrows differently to do subtraction rather than addition. You want to just try like a little example of bitwise subtraction? What about 10101 minus 00110? Just to make sure everybody remembers how to subtract. You start on the right side. I go 1 minus 0 is 1. Next. 0 minus 1. Okay, now I have to borrow, which means this 0 is actually interpreted as like a 10, which in binary is like 2. So this is really like 2 minus 1, which is 1. And this guy got borrowed somehow, right? I'm a master borrower. I'm actually not. I'm not good at subtracting numbers like this. I was fine at it in 3rd grade or whenever people learn how to do this. What about this? This is a borrowed 1, so this is actually more like a 0. So this is like 0 minus 1, which again requires a borrow. I'm going to borrow that. The borrow turns this, which was like a 0, into a 1. So this is now 1 minus 1, which is a 0. I think I did that right. Here, this has been borrowed. This is like a negative 1 now. I have to borrow again just to get myself back to square 1. This becomes a 0, and this becomes a 0. Did I do that right? No, this one should be a 1. This borrow is like I got 2 for free, because that's what happens when you borrow. And then it looks like 2 minus. But this has been borrowed already, so it's really 1. 1 minus 0 is 1. It's confusing to me. You have to think digit by digit how this is supposed to work, though. See what you think. It might be easier if you think of it in this way. If you have no borrow, what is 0 minus 0? What is 1 minus 0? What is 0 minus 1? 0 minus 0 is 0, and again, no borrow. 1 minus 0 is 1, and again, no borrow. This is one way you could try to work them out, digit by digit. And then you have also borrow. Sorry, I'm writing a lot here. I'm going to scroll back to the picture. Feel free to chat with your friends. Remember your youth when you knew how to borrow. Subtract numbers? I don't really. You definitely should start with that.
This is right so far.
Maybe. Yeah, right. This is the one that you makes us start. I didn't write much. You mean those?
Yeah.
All right. Great. So far, yeah. I think of this as when you borrow, it becomes like a negative.
So like this. So for borrowing,
And
it's
then
two.
borrow again.
Two minus one.
It's like a 1. It's a negative 1 and then you borrow and you get 2. I don't know.
Professor, you got a call and you just went away.
A call?
It said from Jennifer Stecker.
Yeah, the wife.
The wife. They're on vacation this week. They went to, she's in San Francisco. Yeah, they left me here. Today's like the public school in Fairfield is on spring break this week. Missed call. All right. That's what I say to that. Doing okay again? This is great so far. Thank you.
Oh,
yeah,
sorry.
this is what makes you wrong.
No. That's,
0, 1.
What about this part?
yeah, but what do I put place?
Yeah, I'm not sure about that.
Yeah, okay. That's
Yeah, I don't think that's
Oh.
Yeah, this is yeah, that's well, this is just one of them.
That's how I
These are borrowed. This is borrowed. This one is actually like this. But then you don't have elements. Any arrows here? I like all this is good. I think
you would have borrowed,
something which
so it's a
something like
negative.
that. It says 1, 0.
So you have to borrow again.
That's what act like 0. But anyway, then you subtract zeros like that.
So 0.
So take that. Not 0.
1.
You don't have all of them. Good.
Yeah, I had 1 to that.
Wait, so
Oh, because that's right.
Yeah.
If 1 is being borrowed, then it
So,
becomes
I
0.
was confused, like, so you get to the carry,
And if it's 1, 0,
they,
it
yeah,
becomes
just like
0.
add 1 on to these.
Well, it's 0, 1 becomes kind of like this 0 kind of
No, it's 1,
if
0.
you're staying in the state, if you're in the state, you've already borrowed. So we have like 1, 0, 0.
All right, should we talk about this? Did she call back? Oh. Nice. All right. Her flight time changed. They're coming back tonight, and I have to go pick them up at like 11:45 p.m. or something. I'm not into that. At JFK. But she says she just changed flights to 9:45, which is great. Aren't you glad I told you all that? Yeah. Yes. All right. You should all watch my new YouTube video too. Since I'm telling you my personal things, I finally made a video that I thought like more than just myself would be interested in. Check it out if you're interested. It's about voting. Maybe it would be helpful. I don't know if it would be helpful, but maybe I could say something. Let's try to like expand this. What I was trying to get at here is, if you have no borrow from a previous step and you're doing 0 minus 0, you just get 0 as the answer and you don't borrow again. If you do 1 minus 1, you get 0 and you don't have to borrow. The only time when you have to borrow, if you weren't borrowing before, is if you're doing 0 minus 1. This, as I was going around, most people figured this out. In that case, if you're trying to do 0 minus 1, you borrow to make that work at all. And this 0 turns into like 2, because when you're borrowing, you grab values from the next digit up. So this is more like a 2 minus 1, which means you get 1 as the answer, but you had to borrow in order to do that, all right? This is how I think these guys through. And then what about the ones from the borrow? So this means if you're doing 0 minus 0 and you're borrowing, This means that this 0 has already been borrowed from. So really, I think of this 0 as like a -1. And in order to do the subtraction, I have to borrow again, which gives me 2 extra. So this is like -1 minus 0, but I get 2 extra. So this is really like 1 minus 0, which is 1, but I had to borrow. So this is my reasoning. I don't know if this makes sense to anybody but me. I would never teach a child how to borrow, explaining it like that, but this is how I, as a man, understand borrowing. You are free to understand borrowing differently. All right? What about 1 minus 0? If there has been a borrow, it means this 1 is actually like a 0. But then I can actually do 0 minus 0. I get 0, which requires no more borrowing. So here, the answer is 0, and I do not have to borrow in the next step. That's because this one, having already been borrowed, is like a 0, but you can do 0 minus 0 without another borrow. All right, what about this 0 minus 1? Having been borrowed, this 0 is really like a -1. -1 minus 1, I'm going to have to borrow to make that happen. Then it becomes something like, I get 2 for free when I borrow, so it's more like a +1 minus 1, which is 0, but I had to borrow. And then finally, 1 minus 1, if this were borrowed, then it's really like a 0 minus 1. I have to borrow, which makes it a 2 minus 1, which gives me an answer of 1 with a borrow. I hope that those are all right, but this is how I think of these. If those make sense, you can translate these directly into the diagram. So first I do this, would you mind if I just say like star, star, R, and then blank, blank, L? This moves me all the way to the right. And then let's say this is my no borrow state. This is my borrow state down here. So I have loops on the no borrow for 0, 0 with answer 0, moving L every time. 1, 0 with answer 1, and 1, 1 with answer 0. And then I have this arrow here with a label of 0, 1, answer 1. Like that, all right? As I was going around, it seemed like most people arrived on this. It's the harder part to think through is what happens in the borrow state. And following what I've already reasoned out over here. 0 minus 0 gives me an answer of 1 and back to the borrow. So that's a loop, right? 0, 0, answer is 1 and loop back to the borrow. 1, 0, answer is 0 and go back to no borrow. 0, 1, answer is 0 and stick with the borrow. And 1, 1, the answer is 1 and stay there. So this is what I got. This I consider confusing just because borrowing is confusing. All right, we should also think about what happens at the end. You know, we had in the addition one, we had this extra arrow about what if you carry all the way to the end. You have to make the last digit into a blank, into a 1 at the end. You should wonder, what if I borrow all the way to the end? Did anybody think about this? Yeah?
I thought about it, but I don't know.
Okay, she was just saying yes. I thought about it. Anybody have a sophisticated response to your thoughts about this? Yeah.
I think like you have to rewrite like a blank on the first, like
On the other side?
on the very left. Yeah.
Oh, on the far left? Change a blank to a 1?
No, change the first digit to like if you step down.
Oh, blank the first digit.
I don't know. That was my.
This is kind of like, can we just maybe think of an example in base 10? I'm just going to make something up which maybe has a lot of borrows. Right? This kind of thing is what creates a lot of borrows. But I'm trying to do this in base 10 just because it's easier. I would borrow, actually I don't really know how to borrow in base 10 either, but I would borrow here to make 9 and then somehow borrow here. I would get that, right? I know what the answer is supposed to be. I don't know what the borrows look like. Okay? Actually, this is not an example where I borrowed all the way to the end, right? Because it didn't borrow all the way to the end. What does it look like if you borrow all the way to the end? That would be somehow like if this digit was also a 0. Then I really would borrow all the way to the end. then it would be negative. Yeah, I think the simple answer to my question about what about borrowing all the way to the end is, if you actually borrow all the way to the end, it means the answer is going to be a negative number, and I said to disregard that situation. All right. You might think, oh well, if I borrow all the way to the end, maybe that just means I write a minus sign right here. Is that correct? No. 0 minus 1 is not negative 9999. It's negative 1. So actually, if you want to correctly handle negative numbers, you have to do something completely different. These individual digits will all be wrong if the answer ends up being negative. So let's not even get into that. The fact is, I said here, assume that the answer isn't negative. That guarantees it's never going to borrow all the way to the end. And so you don't have to worry about that eventuality. All right? Although I happen to know, if you try and do this 0 minus 1 on like an old-timey mechanical adding machine, the typical behavior for those, some of them were designed to handle negative numbers, but the more simple ones, they will actually give you all 9s as the answer, because every digit is just on a little wheel that has 0 through 9 written on it, and all those wheels will turn back by one click, and they'll all say 9. So that there's something that kind of makes sense about this as an answer. But that is not the typical way that we represent negative numbers. All right. This is the last example that I wanted to do of these kinds of Turing machines that compute functions. You'll have plenty of examples on the homework to try these out. Anybody got questions about this? All right, great. I'm going to talk about some more theoretical considerations then. I want to get back to our big sort of hierarchy of languages that we've talked about for a few times. There's the regular languages. This big sort of Venn diagram, but it's not an interesting Venn diagram with overlaps. It's just like nested things. But the terminology, we have terminology for a language of a DFA is called regular. And then a language of a context-free grammar or a stack machine is called a context-free language. That was the next category. And then there is the language of a Turing machine, and that has a name too. So maybe I will say, I'll just tell you what it's called. This is a strange name. It's not called like a Turing regular language or something like that. A language is called recursively enumerable. This is what you call it when it's the language of a Turing machine. Recursively enumerable. If it is the language accepted by some Turing machine. They are called recursively enumerable, and I am basically always going to write RE for recursively enumerable. This language actually comes from the treatments by Alonzo Church. This is a name that I mentioned once. There was another guy who had similar ideas to Turing, but he didn't describe it in terms of abstract machines. He described it in terms of abstract functions that were composed together with each other, which he called recursive lambda functions. And in his terminology, these languages are called recursively enumerable because this is called the lambda calculus approach. In the lambda calculus viewpoint on languages, it makes sense. This name makes sense because it's modeled by recursive functions. In the Turing machine language, this seems kind of out of nowhere, but that's where the words come from. So these languages are called recursively enumerable. It means it is the language of some Turing machine. But there's actually kind of a subtlety here, which I would like to talk about. In a Turing machine, on a Turing machine, there's two kinds of non-accepted strings. And this is a difference between Turing machines and, say, DFA, NFAs. This strange technicality doesn't exist for DFAs or for grammars. Two types of non-accepted strings. So first type is rejected, where the machine stops in some non-accepting state, right? This is the typical way that a string is not accepted by a Turing machine. The machine just stops because it has no arrow to go on for the next part of the string. All right, this is, and actually almost every example we've ever talked about, this is the typical way that a string fails to be accepted. But there is another way that a string could fail to be accepted. There's two kinds of non-accepted. One is when the machine stops in some non-accepting, sorry I forgot to write, state. The other is where the machine runs forever on some string. It is possible for a Turing machine to just run forever, have an infinite loop. This is not possible on a DFA. You can imagine it like a DFA diagram might have a loop in it, but your string is only so long, and you might go around the loop a few times, but you're going to stop eventually when you get to the end of the string, right? In a Turing machine, this is not necessarily the case, because the head of a Turing machine can move right and left. And you can imagine a Turing machine might just go back and forth, right and left on the tape forever without ever reaching the end of the string. It's not hard actually to make examples like that. Sometimes the machine runs forever in an infinite loop. Here's a simple example like that. How about, I got two states, well, I have 3 states total. Let's make this Turing machine. All right. So this Turing machine has some weird behavior, but it's still actually possible to say. What is the language of this machine? So this Turing machine accepts I think the way to, certainly if you begin and the first letter is a B, it's automatically accepted, right? Because you go down this arrow, then the Turing machine, as soon as you reach the accepting state, it just stops and the string is accepted. So this Turing machine accepts anything starting with a B. It accepts, come on now, BX for any X, right? What if the string starts with an A? For instance, can anybody say, what if it's just A? The whole string is just A. Is that accepted or rejected or what?
Rejected.
Rejected, yeah. What happens is, you see A first, you go over here, and now the head is looking at a blank because it moved to the right by 1. And then there's no blank arrow here, so it just stops rejected, all right? Okay, what about an A followed by another A? The same thing will happen. You read this A, and then from this state you see an A, and it's rejected. Okay, so this rejects A and AA, and I guess it also rejects, in fact, AAX, wouldn't it? If you see an A followed by another A, it's rejected. It doesn't matter what else is on there, right? Because you read the first A to go here, the next A makes you stop and reject. And then whatever else follows really doesn't matter at that point. All right. Also blank, just blank, the empty string, that's also rejected because you get here and there's no arrow for a blank. So I'll put that in there. Empty string, A or AAX. What about A followed by B? Let's try A, B. If I were to write this down using my, derivations specifically, I'd write it like 1AB. Sorry to scroll that guy. Come on. In state 1, I see A. I'll make it an A and move to the right, so it now says A1B. Now, sorry, 2, because I changed to state 2. Now I'm in state 2, I see B. I go this way. This is a BBL, so the B stays as a B. Move the head to the left and change to state 1. That means this 2 goes back to the left and changes to state 1. It becomes 1AB. How you like that? We are now in exactly the same state that we started, and so it's going to do this again, right? The next step will be A2B, then it will do 1AB again, etc. This is an infinite loop, all right? So this makes an infinite loop for any string. Actually, ABX. Like if you see A and then B, that's what causes this infinite loop. If there's more stuff after the B, it doesn't even matter. That stuff will never get, the head will never encounter that stuff. It will still just be going back and forth between the A and the B at the beginning, right? So this makes an infinite loop for any ABX. All right, this is actually a complete description of the language of this machine. So if I were to write this more formally, we would say the language of M, this is all strings which are accepted. That's BX, where X is in AB star. That's the very first thing we said. If it starts with a B and has anything else, it's accepted. Then we have two other languages, really, two other sets. There's the ones which are rejected outright, and then there's the ones which cause an infinite loop. And these are going to be called R, and our book calls it F. F maybe for forever. You can't use L for loop, so because I already used L for language. So the rejected strings are, whatever I said, epsilon A and AAX. I'll just write AAX. X and AB, and also epsilon and A. Those are sort of special cases, but generally speaking, the ones which are rejected are ones which start with two A's, right? And then there's the ones which loop forever. So these are rejected. And then there's the ones which loop forever, which is anything starting with AB, followed by X. And these are the ones, these are the infinite loops ones, all right? So a Turing machine, like I said before, you don't ever need to worry about this for DFAs because a DFA cannot have an infinite loop in it. A DFA can have loops in the diagram, but you can't go around the loop forever because a DFA only reads one letter at a time to get to the end of the string. But these guys can have an infinite loop. And I think that's all the time we have for today. More on this next time.